So hi friends, this is your Prashant sir. Welcomes you to the world of physics from KH Patel PU College, Hubballi. So today in my 7th lecture, I am going to discuss one of the most important concept as nuclei chapter is concerned and as the examination, board examination is concerned. Listen carefully, the board examination is concerned. This concept is very important. That is nothing but binding energy curve. Binding energy curve. So in previous lecture, I am discussed about one of the most important concept, that is nothing but mass defect. Then we have also discussed what is meant by binding energy. Then we have also discussed binding energy per nucleon. So binding energy per nucleon is nothing but the amount of energy required to break one nuclei. Either it may be proton or it may be neutron, but the amount of energy required to break one nuclei from its nucleus is known as binding energy per nucleon, and it is given here. That means for nucleus, binding energy per nucleon or specific binding energy is defined as the ratio of binding energy of the nucleus to its mass number. So binding energy of the nucleus to its mass number, the formula is given here. That means binding energy per nucleon is equal to binding energy divided by atomic mass number. Here the binding energy is nothing but the amount of energy required to break up or required to break completely the nucleus into its constituent nucleons. The amount of energy required to break completely a nucleus to its constituent nucleons is known as binding energy divided by atomic mass number. This atomic mass number is nothing but total number of nucleons present inside the nucleus. That means the sum of protons and neutrons present inside the nucleus. So this ratio will gives you the binding energy per nucleon, or in other words it will be specific binding energy. So we have discussed up to this in last class. In today's class, I am going to discuss one of the most important, one more important concept, that is nothing but binding energy curve. First of all, what is meant by binding energy curve, which is given here? Binding energy curve. It is the curve obtained when a graph of specific binding energy, which is along a y-axis, is plotted against the mass number. Which is along y-axis. That means it is this binding energy curve is a curve obtained when a graph of binding energy per nucleon or specific binding energy is plotted against the mass number. So when we plot a graph of binding energy per nucleon or specific binding energy against the mass number, whatever the curve obtained, that obtained curve is nothing but binding energy curve. So this binding energy curve explains so many things to us. By looking this curve, what are the I will just try to explain what are the different characteristics of this binding energy curve. This is only the very important part as binding energy curve is concerned. That is nothing but the characteristics of binding energy curve. So first of all, so as we know, for lighter, that means the atomic mass number is less and atomic number is also less. Such a nuclei are known as lighter nuclei. That means we will consider, if the nuclei with atomic mass number less than 30 will considered as a lighter nuclei. And heavy nuclei, for heavy nuclei, the atomic mass number will be more than 170. If the atomic mass number for a nuclei is more than 170, then that will be considered as a heavy nuclei. And if the atomic mass number is less than 30, then those elements, those nuclei will be considered as lighter nuclei. For looking this graph, it is clear that for lighter nuclei and for heavy nuclei, the specific binding energy is very less. For lighter nuclei and for higher nuclei, the specific binding energy or binding energy per nucleon is very less. So look at here, for in this region, and in this region. So this is the region in which the binding energy, so this is the region where the nuclei has the mass number less than 30. So in this region, clearly look at here, in this region, the nuclei has the mass number less than 30. So coming to in this region, the mass number has more than 170. So it will be more than 170. These elements has less binding energy. So for example, hydrogen 1 2, here it is hydrogen 1 2, sorry, here it is hydrogen 1 2. It has less binding energy because it will be represented here. And hydrogen 1 3, this is also has less binding energy. Helium 2 4, lithium 3 6, carbon 6 12. These are some elements which have less binding energy per nucleon, or binding energy, sorry, specific binding energy is very low because these are lighter elements. And for heavy elements, look at here, uranium 238. So it has less binding energy per nucleon as compared to the other nuclei. So I just want to explain one thing, that the lighter nuclei, the nuclei with mass less than 30, and the heavy nuclei, the nuclei with mass number more than 170, for those the binding energy per nucleon is less. So one thing we have to know, that if the binding energy per nucleon or the specific binding energy per nucleon is less, means they are less stable in nature. That means if the binding energy per nucleon or specific binding energy per nucleon is more, means they are more stable in nature. That means if the binding energy per nucleon is more, then we have to invest more amount of energy to break the nucleus. Right? The large amount of energy is required to break the nucleus. If the binding energy per nucleon is less, then the less amount of energy is required to break the nucleus. That means if the amount of energy required is less, then those elements are less stable in nature. If the amount of energy is required to break the nucleus is more, then they are more stable in nature. So this we have to concentrate. So this we have to understand. So what binding energy explains means, it will be related to the point of stability of the nucleus. How much stability the nuclei has. If the binding energy is more, such elements are more stable. If the binding energy is less, such elements are less stable. That means the amount, the nuclei with mass number less than 30 and the nuclei with mass number more than 170, they has less binding energy per nucleon. That means they are less stable in nature. Less stable in nature. Is this clear? So the amount of the nuclei with mass number less than 30 and the nuclei with mass number greater than 170 are less stable in nature because their binding energy per nucleon is also less. That means the little bit amount of energy is required to break the nucleus. So this is one of the most important characteristic of this curve. So this curve clearly explains, listen carefully, this curve clearly explains for lighter nuclei and for heavy nuclei, or the nuclei with mass number less than 30 and the nuclei with mass number more than 170, they have the less binding energy, therefore they are less stable in nature. Is this clear? So yes, one more important characteristic this curve has. So in lighter nuclei, that means in this region. So in lighter nuclei, that means in this region. So there will be one more important characteristic this curve has. So the nuclei with even number of protons and even number of neutrons. Listen carefully, the nuclei with even number of proton and even number of neutron is more stable than their neighboring elements. Or the nuclei with even number of protons and even number of neutrons is more stable than the nuclei with odd number of protons and odd number of neutrons. Is this clear? The nuclei with even number of protons and even number of neutrons is more stable than the nuclei with odd number of protons and odd number of neutrons. So just have a look here. So there will be hydrogen 1 2. Hydrogen 1 2. Have a look here. Here it is hydrogen 1 2. So hydrogen 1 2 has one proton and one neutron. One proton and one neutron. Both are odd numbers. That means hydrogen has odd number of proton and odd number of neutron. Therefore, the binding energy per nuclei is very less. So if the binding energy per nuclei is very less, means it is less stable in nature. Less stable in nature. So coming to the point of helium-24, here it is helium-24. For helium-24, suddenly the binding energy increases. Binding energy per nucleon increases. It reaches approximately more than 6. More than 6. Binding energy per nucleon becomes more than 6. Is this clear? So that means for helium, if you concentrate on helium, it has 2 protons and 2 neutrons. That means even number of proton and even number of neutron. Therefore, the specific binding energy or binding energy per nucleon is more for helium. That means it is more stable than hydrogen 1, 2. Hydrogen 1, 2. Because hydrogen has odd number of protons and odd number of neutrons, it will be less stable as compared to helium, because helium has even number of protons and even number of neutrons. So coming to the, we'll take one more example, coming to the point of lithium-36. Here it is, lithium-36, sorry, here it is lithium-36. So lithium-36 has the 3 protons and 3 neutrons. That means odd number of protons and odd number of neutrons. So for this, as compared to helium, suddenly the binding energy decreases. Here it is, have a look here, here it is. Suddenly the binding energy decreases. So if the binding energy decreases, means if the specific binding energy decreases, means it is less stable as compared to the helium. It's less stable as compared to the helium. And again, let us consider one more example for carbon 612. Here it is, carbon 612. Again, suddenly from lithium to carbon, the curve increases. From lithium to carbon, curve increases because carbon has 6 protons and 6 neutrons. Even number of protons and even number of neutrons. So the binding energy per nucleon or specific binding energy increases. Therefore, carbon 612 is more stable as compared to lithium-36. Is this clear? And for nitrogen 714, again the specific binding energy decreases for nitrogen 714. Again the specific binding energy decreases. That means binding energy per nucleon decreases. That means it is clear that nitrogen is less stable as compared to the carbon. Because carbon 612 has even number of protons and even number of neutrons, therefore it will be more stable. Nitrogen 714 has odd number of protons and odd number of neutrons, therefore it will be less stable. Or the binding energy per nucleon is less for nitrogen as compared to carbon. And again for oxygen, oxygen has 8 number of protons and 8 number of neutrons. That means even number of protons and even number of neutrons. Therefore, the binding energy per nucleon again increases for oxygen. Therefore, oxygen is more stable as compared to nitrogen. So these examples clearly shows that in lighter elements, in lighter nuclei, the atom with even number of proton and even number of neutron has higher specific binding energy as compared to the atom with odd number of protons and odd number of neutrons. So for the nuclei with even number of proton, even number of neutron, the specific binding energy is high, means these are highly stable in nature as compared to the nuclei with odd number of protons and odd number of neutrons. So this is one of the most important characteristics of nuclei. This is one of the most important characteristics of binding energy curve in a lighter nuclei region. So once again, I will try to explain in brief. That means the nuclei with even number of protons and even number of neutrons is more stable as compared to the nuclei with odd number of protons and odd number of neutrons, because the nuclei with even number of protons and even number of neutrons has the highest binding energy per nucleon as compared to the nuclei with odd number of protons and odd number of neutrons. So this is one of the one more important characteristics of binding energy curve. So next, so one more important characteristics of binding energy curve is, have a look for this ferrum 56. That means iron 56. Fe is the symbol for iron. Have a look here. Fe is the symbol of iron. So if you concentrate on this iron element which has the highest binding energy per nucleon, which has the highest binding energy per nucleon, and it must be nearly equal to 8.75 mega electron volt. So the binding energy per nucleon, or the specific binding energy of iron, is about 8.75 mega electron volt, and iron has the highest specific binding energy. That means amongst all the elements, iron is highly stable in nature because it has highest specific binding energy. So that means the large amount of energy is required to break the nucleus of iron. So if the amount of energy required to break the nucleus of iron, that means it is more stable in nature. So is this clear? The iron has the specific binding energy of about 8.75 mega electron volt, and it is highest amongst all the elements. Therefore iron is more stable in nature. Iron is more stable in nature. So this is one more important characteristic of binding energy curve. And the atomic number, one more important characteristic of this binding energy curve is the atomic number which is greater than 30, and less than 170. The atomic number which is greater than 30 and less than 170. If you concentrate on these elements, the nuclei with atomic mass number greater than 30 and less than 170, if you concentrate on these nuclei, for those the binding energy per nucleon is nearly equal to binding energy per nucleon of iron. So the binding energy per nucleon, or specific binding energy of such a nuclei with mass number more than 30 and less than 170 is nearly equal to the specific binding energy of iron. So that means it is nearly equal to 8.75 mega electron volt. Therefore these elements are also more stable just as iron. So just as iron is more stable, the neighboring elements such as the mass number greater than 30 and less than 170, those all nuclei have the binding energy per nucleon, or specific binding energy, nearly equal to 8.75, which is the specific binding energy of iron. Therefore these elements are also more stable such as iron. Iron thara ee ella elements kuda stability ಜಾಸ್ತಿ ಇರ್ತದ್ರಿ. But the atom with mass number less than 30 and the atom with the mass number more than 170, for those the specific binding energy decreases. Therefore they are less stable in nature. So is this clear?